Okay. So, I wanted to talk about another concept because there is definitely a reason that computer language has evolved the way it has, just because of the way that number systems works and the way that we're processing our bits and our bytes and how we're basically combining and collecting these things so we can make the computers like process the information a little bit easier and go through the whole concept. So as we went through the slide deck, we did talk about the fact that a byte is 8 bits, and this is very significant because as you kind of go through the process of looking at that, each byte being a total of 8 different values like that, right? Um, if we cut that in half and we use 4 bits, we can actually do a transition to where 4 bits can actually be represented by what's called a hexadecimal number. Because in decimal, we actually have 10 different representations using the numbers 0 through 9, right? You have 10 different pictures or representations for each place value. But in hexadecimal, we need to have 16 different ones to represent that. So we need to have 6 additional ways to actually show something in a given place. So we start actually using letters, right? So as we go through this process, right? Initially, when we're using hexadecimal, we use the normal numbers that we actually see in decimal to do those representations. And I have used the term base conversion, right? So, mathematically, when we show different bases and everything, because right now you don't know if that's really decimal, because normally when we write numbers, if we don't actually put something at the base of it, it's always understood as decimal. So if you ever see a little number there, that actually gives you a representation of what the base value is. So if you see a 16 down there, that actually means that is a hexadecimal number. If we were to put 2's underneath there, that would actually show that this is a binary number. So you would actually know that's a binary number. So our initial 10 values in binary can actually use those 10 digits that we normally use in decimal, but they're also used in hexadecimal. So now, when we get to the position of 10, oops, if we want to represent it in a single place, we have to use a new type of shape or number. But since we don't have numbers that already exist, what we ended up doing was we started using letters, right? So 10 in a single place value is actually an A, and then we go through. 11 is B, 12 is C, 13 is D, 14 is E, and 15 is F. Okay? So, anytime that we're actually talking about hexadecimal, we have to add these 6 new shapes or characters. So what we ended up doing was we used the alphabet to actually go into hexadecimal. So anytime you actually start to see letters in your placeholders, you'll know that we're actually talking about hexadecimal when we start using letters, because that's the only time that we actually, in our number systems, we start using letters, other than algebra, right? But that's a variable, which is a completely different concept. If we're actually giving set values and everything, we're actually talking about hexadecimal. So if you see a single value where you're actually seeing A through F, we're actually talking about a hexadecimal number. Now this is important because when we actually talk about a byte being 8 bits itself, we actually also use the concept of what's called a hex pair, because since a byte actually has 8 bits and a hexadecimal number represents 4 bits, we can actually use a hex pair to represent any given byte of information, right? So let's say you see a hex pair of A7. A7 actually represents 1 0 1 0 0 1 1 1. But in the hex pair right there, that first one of the hex pair actually represents the higher value order in that byte, right? So this is actually not a one place. This is an actual 16s place. This holds a value of yes, 16, 32, 64, and 128 is that higher order in the hex pair itself. And this is significant because anytime we actually have a byte, right, of information, you can actually have a total of 256 combinations. And one thing that we actually talk about when we actually give bytes of information, those 8 bits, it's very significant in everything that we actually do in coding, especially in gaming. Like in gaming, you will hear the concept of like 8-bit technology, 16-bit technology, 32-bit technology, 64-bit technology, and it's literally talking about channels of information that are going through using those byte values on how your game system or your computer actually processes the information. So especially when we start to talk about like visual color, we actually use those bits in such a way that it gives us a different value. So I have like an expanding question on your questionnaire there and everything that goes into the concept of when we talk about color. We always talk about 24-bit color. because 24-bit color actually talks about the three channels of color that exist in visual color, which is your red, your green, and your blue channels of color. So you hear RGB all the time, but it talks about the red channel, the green channel, and the blue channel. And the reason that a byte is very significant is because with a byte, since you have 8 bits, uh, each of these channel uses 8 bits. So that's what actually gives you 24-bit color, because each of these channels has a total of 8 bits in it. So 3 times 8 is your 24-bit color, and that bit represents any value from 0 to 255. So a lot of times when we're actually coding and we're trying to represent RGB, you will have values anywhere from 0 to 255. And that actually gives you a huge amount of possibility of different variants in colors. And when we actually go into digital color theory and everything, you'll notice that that gives you so much variations of colors that even the human eye really can't recognize a lot of the differences. Now, a big concept is you hear the term 32-bit color talked about a lot, and 32-bit color is a whole nother concept of where we're adding what's called an alpha channel, and the alpha channel doesn't invent a new channel of color. What it actually does is it adds the concept of opacity into our given variance of color, and opacity actually allows the way that colors are actually looked at as a combination or as a full composition of color and everything. So the way that the eye actually takes in the information and looks at it, when you start to play with opacity on the alpha channel, it actually it gives you a different sense of color, because what you're actually seeing is the relationship of colors as they become a little bit more transparent or less opaque, and it gives you a optical illusion that it's a different color, but we haven't added more color to it, or we just added different variances to it, to the way that your eye actually sees it. So 32-bit color is just adding an alpha channel of information, and that's what it actually is.